Hello everyone, today we will talk about our final project, Hyperdimensional Generalization, a creation of a hyperdimensional snake game agent. First of all, let me introduce our new snake game. Original snake game will like this. The player controls a long thin creature resembling a snake, which roams around on a boarded plane, picking up food, trying to avoid hitting its own tail on the edges of the playing area. Each time the snake eats a piece of food, its tail grows longer, making the game increasingly difficult. We suggest a new form of generalization, hyperdimensional generalization. We will show overcoming the barrier of dimension by reinforcing learning with graph neural network on snake game. However, if original rule is followed, the game will often end before the snake is the apple, which will take a lot time of train. Therefore, we implemented the game to restrict moving to touch the wall or its own body. The snake in our restrict snake game dies only when it cannot move in any direction from its head. For convenience, snake game in our presentation will denote the restrict version. Our goal is to find a general agent which behave well among different dimension and size. Since there does not exist 3D snake IO, we built our own 3D visualization. So how could we make a desired agent? We use reinforced learning, especially A3C, an abbreviation of asynchronous advantage actor critic. A3C is a deep reinforcing learning algorithm that asynchronously updates the neural network using multiprocess. A3C is fast trained and requires only a single multi-core CPU. Our available resource was not so enough and we have very limited time to train. So we decided to implement A3C algorithm, and we have to implement a neural network that composes a decoder of A3C. Since we aim to make an agent that plays well on various sizes and dimensions, we should think about what would happen when the size or dimension of the board is changed. For example, if dimension increases, action space will change. In classical CNN, we need a fully connected layer that translates to a fixed action space, which fits our model. Since CNN only handles fixed input, then to manage variable sizes, we can consider the NLP problem. Because they treat the one-dimensional sequences, they require the board to flatten to one dimension. Then it will not distinguish some totally different boards which flatten to the same number of cells. So we need a way to represent a relationship between cells on the board with various sizes and dimensions. The solution is graph neural network. By GNN, a snake game board can be represented as a graph by treating each cell as a node and agency as edge. This way, any structure with a different dimension and size will be determined by GNN. GNN is usually used for making a decision by watching local space. Hence, on a large snake game board, message passing cannot reach. In this situation, the snake does not know where the apple is located. To solve this problem, we came up with a new form of GNN layer, global GCN. Global GCN will collect a little message from a node far away in the graph. But this way, too much messages will be received from every node, or a smoothing problem might happen. Thus, we have to mix local and global GCN to fix it. The figure is the architecture we used so far. But global GCN only compares messages of same type to cells with a scale. But this is so insufficient that we cannot distinguish which region it came from. Therefore, we need a better method to figure out the source. For graph positional encoding, we found GraphFormer and GLPE, which reflects distance between nodes on attention calculation. In this project, we used the GLPE version of spatial encoding and GraphFormer layer, which is graph version transformer. Following expressions are GLPE attention. Finally, we used this policy and value function and provided it to A3C. These are some notations we used. To achieve our goal, we trained with each one full 7 boards with GCN, local and global GCN, GraphFormer, and GAT9 models. We evaluate those models on 3 cases of trained board, 2 of larger board, and 4 for similar board. After that, we chose best model and played randomly 1000 times to show poor probability. The most important point is that we used different board set during training and test. These are some example training logs. We use the shortest path as a baseline. If there exists a way to eat an apple, the shortest path always exists, and the snake is guaranteed to eat the apple along the path. And if there is no way to eat the apple, it randomly moves and finally dies without eating an apple. Also, we considered randomly moving agent and transformer version A3C trained agent. Their performance is provided on the slide. For 9 agents that we trained, we plot graph that represent the score distribution of 1000 two-dimensional 10 tests. This figure denotes the difference of performance when agents are trained on the different train sets. On each graph, colored vertical line denotes the mean score of the agent that was trained on the specific train set or is moving along the shortest path to the apple. Since 2D 10 board is contained on every train set, it shows how much an agent does well on the trained environment. When you see the vertical perfect score line of the rightmost graph, an agent using GraphFormer and trained on the train set 1 shows a perfect score on above 30% cases. This figure denotes the performance of the agent. They use different GNN layers. Agents using GraphFormer show the best performance on every train set. All agents that were trained by A3C algorithm show better performance than the agent moving along the shortest path. This table lists numeric scores. Train set 1 shows the best performance on every layer, which we think is because the agents are optimized on 2D 10 board since they were trained only on that board. On GCN and GraphFormer, the performance decreases as the train boards become various, and on local and global GCN, performance are similar to that of GCN, but more consistent on different train sets. The best way of making an agent on specific dimension and sized board is training the agent with GraphFormer on only one board that will be tested. For 9 agents that we trained, we plot graphs that represent the score distribution of 1000 3D 5 tests. Since an agent is not trained on 3D on the train set 1 and 2, it can determine how much the agent is generalized hyperdimensionally. This figure denotes the difference of performance when agents are trained on different train sets. An agent using the Jisung layer with train set 1 failed to eat even one apple on above 30% cases. Hence, it shows worst performance, including even the short path agent. Jisung failed to generalize hyperdimensionally. This figure denotes the performance of agents that use different GNN layers. Score distribution on 3D5 board. Graphformer showed the best performance on every train set. Also, the perfect score is obtained only using Graphformer. You can check that every agent shows higher performance than the shortest path except one case, so hyperdimensional generalize actually works. This table lists numeric scores. As you can see that performance on train set 2 are better than on train set 3. A larger and various train set is not always good. Overall, we found out that agent with GCN and local and global GCN show similar performance if they are trained in the proper environment, and agent with Graphformer show the best performance wherever it has been trained on. But except the agent with local and global GCN, agent on the train set 1 failed to generalize hyperdimensionally. This is the training log of the agent with Graphformer on train set 1, which show very unstable performance. Agent on train set 2 and 3 shows stable performance, but agent on train set 2 shows better performance and took less time to train. As a result, the agent show hyperdimensional generalization. Still, there was not enough time to train, and the performance of the agent did not actually converge. As you can see on this training log, the performance is still increasing after 60 million steps even if we have waited for 5 days, and still increasing even after waiting for 4 days. Since the agent take days to train, we couldn't do hyperparameter tuning enough. They are underestimated and their performance could be better. And to conclude, we showed that hyperdimensional generalization works by ally with GNN on Snake game. Also, we experienced it and learned the reinforcement running and graph neural network that are beyond the coverage of CX376 and how much time our research takes, which was meaningful time to us. These are some succeed graphics provided by our project. Our Snake agent has successfully cleared the stage. Following is our reference. Thank you for listening.